Welcome back to Stewart Science. Today we're talking about how we represent energy by using bar charts. And so we've already talked about how there's different forms of energy, but today we're going to represent them graphically using bar charts. And so another name for this video could be energy bar charts. Now, I actually have a different name for these. I call them LOL graphs because the first L stands for the energy at the beginning. That's a bar graph. The O, as we'll see today, is the flow, if the energy is going in or out of our object. And the second L is the energy and where it's at and how much energy is in each form at the end. So all of the examples that we're looking at today are going to have two scenarios, like a before and an after. And sometimes that energy is going to change ways and be in the same object, so it'll change form but stay in the same object. Sometimes it'll either go into the object or out of the object. And so I'm going to give us a bunch of different examples and how we represent that. So first of all, this is the basic structure that you're going to see for problems like this. This just helps us categorize our energy. And so EK is kinetic energy. EG is gravitational energy. EL is elastic energy. And you can say we have the same forms at the end. So EK, is it moving? EG, is it raised up? And EEL is something being stretched or squished. Now we have an extra form of energy over here called E internal. Another name for this could be E thermal or E dissipated. This is the energy trash can, so to speak. Anytime energy changes hands, some of it is not going to end up in the right bucket on the other side. So whenever you convert energy from one form to another or from one object to another, there's going to be some energy lost. Sometimes that's not very much energy and we don't even need to think about it. Sometimes it's a lot of energy. And so if you ever think about something stopping because of friction, friction makes heat, and that heat is wasted. It's energy that kind of like goes off into outer space, where that means dissipated, or it's heat, which means thermal. So this is kind of like the energy trash can, this column over there. So here's the first example. If we start with a ball that's rolling down a hill, really these arrows aren't drawn right. It should be, this is a short arrow, and this is a long arrow. Because it should gain speed at the bottom of the hill. So that's what I want to show here. We're going to use these different categories, the EK, the EG, the EL, to think about how much energy the car has, or the ball has here at the very top of the ramp. And so since the ball is up off the ground, it's elevated compared to the ground, it's going to have some gravitational energy. And since the ball is moving a little bit, we're going to give it some kinetic energy too. So we've got, we'll say, one box of kinetic and one box of gravitational. And I'm not looking for anything super exact here. I'm just looking for general ballpark accuracy. Now, I wouldn't put anything in this category because there's nothing being squished or stretched in this picture. So we have some kinetic because the ball is rolling already. You can see there's a little arrow at the beginning. And some gravitational because it's up off the ground. Now, at the end here, if we skip over this middle part, we'll come back to this later. If we skip over this and go to the other kind of energy, the final scenario, our ball is moving faster, but it's lower. So it's no longer raised up, so we don't have any gravitational energy anymore. It's still not squished or stretched, so we don't have any elastic energy, but it's moving faster, so now it has more kinetic energy. So what you're trying to represent here is what's called the conservation of energy, which means that energy can't be created or destroyed. All the energy that you have at the end, you also have at the beginning. And so you shouldn't have a different number of boxes at the beginning and the end. You can see here we've got 1 and 2 for a total of 3 boxes on this side. And then we also have 3 boxes here because we have none there and none there. So we started with 3 and we ended with 3. Which means we've conserved our energy. Our energy didn't gain or lose anything during this example. Let's do a bunch more. So this is a classic catapult. And so you can see these are some rubber bands right there. And so, as we said before, anything with a rubber band has what's called elastic energy. And so since the ball isn't moving at the beginning, and it's not really off the ground very far, and maybe you could say this is a little bit off the ground. So if you had some there, this is pretty flexible, but I'm just, general ballparking this. It's not very high off the ground. We're going to call it no gravitational energy. And since, all catapults, they start at rest, there's no kinetic energy either. And so all of our energy that we have here at the beginning is just in the stretch of our catapult. So we start with 3 boxes of elastic energy. So all of our energy is in the stretch of those rubber bands. Now, once the catapult's released, now you can see we have some height here. The ball is off the ground, so we're going to need something in this category. And it's moving, so we're going to need some in this. And this is where that flexibility comes in. So if you want to say that this has 2 boxes of kinetic and 1 box of gravitational, because it's off the ground and it's moving, I'll take that. If you want to say it has 1 box of kinetic and 2 boxes of gravitational, I'll take that too. Because the point is, you're representing the fact that now that ball has energy that's in 2 ways. It's moving and it's elevated. And so you show that by having some here. Now we have no more elastic energy because our rubber bands here are no longer stretched out. And so the elastic energy that was there at the beginning has now been changed into the kinetic and gravitational energy. And there wouldn't be any internal energy. That's something you only use when it's obvious that the energy has gone into the trash can. So let's try another example. This is a box that's rolling, or sliding, down a hill. Now, if it was rolling, there wouldn't be very much friction, but since it's sliding, we know there's going to be some friction. So since there's no lines here to show at the beginning, all of our energy is gravitational. And it's a little bit arbitrary how many boxes you want to give it, but 3 feels good. So it's all gravitational. It's not moving, and there's nothing being stretched or squished. So at the beginning, in the first initial state, the energy is 3 boxes of gravitation. Now, in the final state, we can see it's moving, and it's lower. So since it's on the ground, there's no more gravitational. That's gone. It's still not being squished or stretched, so there's no elastic energy either. So there is some kinetic. And again, this is where it gets a little bit, You can say it has 2 boxes. You can say it's a 1 box. I'd say it probably has less than 3 because there's probably going to be some friction there in the surface. So let's say it has 2. In order to add up to our 3 that we had at the beginning, we need to add 1 box to this EINT. And again, you only need to use this internal or dissipated or thermal. Dissipated or thermal. You only need to use that when you can pretty obviously see the energy has been not converted very well. So since there's friction there, it's been sliding, it's going to be slower than it would be otherwise. So we only use this internal trash can category when we can know that we've lost some energy. So this one starts out with all gravitational because it's elevated off the ground, and ends with some kinetic because it's moving, and some internal because there's some friction there. Now, I've added another kind of scenario to the end of this one. So now our initial scenario is the one that we just had, where something's moving. And our final scenario is the box having finally come to rest, having run out of gas, the inertia is 0, and so now it's stopped. And so this one, we're going to have no kinetic because we're no longer moving. We have no gravitational because we're on the ground, same as we were at the beginning. We have no elastic because we're not being stretched or squished. And so all we're left with in this one is all of our energy now is in the energy trash can, EINT, or the E dissipated, or the E thermal category. All of our energy has gone into the energy trash can. All right, now some of these examples will involve energy being put in to the object. And so if you look at this example right here, this woman tossing a medicine ball into the air, if we're just looking at just the ball does not have any energy. Now, the ball is technically in the woman in the form of chemicals before she tosses it. Your body is turning a chemical called glucose into energy. And so there's technically chemical energy in the person, but we are looking zoomed in on one item. It's called our system. Our system in this example is just the ball. And so that ball has no energy at the beginning. It's not moving, it's not off the ground, and it's not being stretched or squished. So at the beginning, the ball has no energy. Now at the end here, it's off the ground. It's probably still moving, maybe not, but it definitely at least has some gravitational. So let's put a box of gravitational there, because it's off the ground. So somewhere around 2 bars, if you want to call it 1, you want to call it 3, whatever, it's fine. It's just communicating. What are you communicating? You have to communicate there's some gravitational energy because the ball is higher at the end than it was at the beginning. And I'd probably give it some kinetic too, because it's probably still moving. We don't really know what's happening in this picture, but it's pretty close. We'll call it that. So here's an issue. If we have 0 and then we have 3, we've broken that conservation of energy. We no longer have conserved our energy. So we need to show somehow, we need to diagram the fact that we've gained energy. Because what happened to make that ball move is that the woman put her energy into the ball. And so we need to show energy go in to our object. And so think about this flow diagram like, is energy going in or out? Is it crossing the barrier into our picture or not? And so if we see the ball, it has no energy at the beginning, and the woman gives it some, we need to show that energy going in. And we need to show how many boxes there are. So you go from 0 to 3, which means you've gained 3 boxes. So we show 3 boxes going in. If you had 4 at the end, you should show 4 boxes going in. If you had 2 at the end, you should show 2 boxes. So whatever the difference is from this side to this side, if it's because you've gained or lost energy, you should show it going in. Now, if this is the other way around, the woman will be losing energy because she's putting it into the box. This arrow will be going the other way. Let's keep going. Do another example. So here's an example like this where we could pick either object. We can look at the spring first, or we can look at the ball. So I'll do one for each. We'll start with just the ball. So that ball at the beginning is sitting on the spring. So you might think, oh, it has elastic energy. Well, what has the elastic energy? The spring has it. So if we're just looking at just this ball and not the spring, there's no energy at the beginning. The ball is not moving. It's not really off the ground very far. And it doesn't have elastic energy. The spring has elastic energy. At the end, you can see the ball is in the air. Maybe it's still moving a little bit. So let's say it's moving and it's in the air. None of this, there's no obvious energy loss. So we have 3 more boxes at the end than we had at the beginning. We need to show those going in. There's an arrow going in because the ball is gaining energy. We need to show 3 boxes going in. Now we're going to do this exact same example from the perspective of the spring instead. So let's try that. Let's look at just the spring. From the spring's perspective, it's not moving. The spring isn't off the ground, but it is being squished. And so it has some elastic energy. You can give it 2, you can give it 1, you can give it 3. I don't care. I'll give it 2 this time. And so the spring has 2 boxes of energy. And again, it's kind of arbitrary. I picked that. If you pick something different, that's okay. It's what you communicate. Some of the energy, in fact, all of the energy the spring has is elastic. Now at the end, the energy has gone from the spring into the ball. So the spring is no longer squished. So it has no elastic energy. You might be tempted to say, well, it has some gravitational because it's off the ground now. But remember, we're just looking at the spring. The spring is still on the ground. And so it has no gravitational energy, and the spring is not moving, no kinetic energy either. And so in this case, we had 2 boxes at the beginning, 0 total at the end. We need to show energy going out and make sure we represent that as 2 boxes of energy going out. So just to wrap things up, in the energy flow diagram, this side is what kind of energy your object has at the beginning. This side is what kind of energy your object has at the end. Those two numbers of total boxes of energy need to be the same. And you can show the reasons why they're not, either because you've gained or lost energy with the flow diagram. That's energy going in or out. If there's only one object and you know there's a difference in the energy, that's probably because energy has been lost in the energy trash can, because not every energy conversion is efficient, which means you probably have heat or thermal energy or something that's kind of sucking away your energy. So you only use this basically if you know that there's friction there. This is what you use if you know there's another object that's giving or taking energy from the system. So beginning, end, any interaction with other objects. This is Mr. Stewart. Keep learning no matter what.